to move the nutrients through the system. And some of those functions we'll look at some diagrams of also are food chains and energy circuits. And then other parts, the components, kind of the building blocks of an ecosystem. And when you start thinking about it, there's things that are not alive, the abiotic factors, and that's physical things like climate and temperature and hydrology, and the inorganic chemicals that are there and the organic compounds. And then you have biotic, or living components, which are broken down into producers, consumers, macro-consumers, micro-consumers. You might have heard some of that in high school or college science. And there's also energy circuits. And so energy is cycled through these systems just like materials are. And so these cycles of materials and energy and these functions build up into trophic levels and food webs, and that starts to build a structure of a complex ecosystem. So the point you're supposed to get out of all this is not the details, but the idea of how complicated it is and how interconnected it is. And so when you're looking at a water quality problem, you can't just look at water chemistry. And that's what most people think of when you say water quality. You have to look at biology, chemistry, and physical aspects. So now we get to the really fun part, the second law of thermodynamics. And the basic part to remember is think about it as a system. If you're biologically oriented, you can think of it as a biological ecosystem. If you're more mechanically or engineering minded, you can think of it as a machine. If you're like an accountant and you're really into numbers and spreadsheets, think of it as a budget. And so the idea is that nothing's created or destroyed. Matter and energy are just going round and round. You can transform energy and matter back and forth. You can change the forms of matter, but you're not creating or destroying everything. So when you're looking at a pollution problem, if you just keep asking this question, you'll get somewhere. Keep saying, where does it go? And just keep saying that, and you get more and more information about what's really happening. So the main thing is that whatever goes in and whatever goes out has to balance. It can have transformation in between, but in the end, everything balances. And that's a very useful concept, because when we want to achieve a certain goal in the ocean, that's the bottom receptor that gets everything. It's at the bottom of the hill. So we have to balance everything going in on the Mauka side with what we want to achieve in our output in terms of ocean water quality. So this is an example of some types of Hawaii water bodies, or aquatic ecosystems would be another word. And this is the way the regulations in Hawaii classify these ecosystems. They call them waterbody types, and there's three main types. There's marine bottom ecosystems, there's inland systems, and there's marine systems. So inland, you have fresh water, and that's broken up into flowing waters like the waterfalls and the streams, and standing waters, which we don't have a lot of in Hawaii, but like lakes and reservoirs, there's very few of those. And we don't have a lot of standing water because we have very porous geology, so it tends to leak out. And then water wetlands. There are both low and elevated inland wetlands. What's interesting and what most people don't know is that a lot of these nearshore ecosystems are actually considered inland, like the brackish and saline coastal systems like the Anchialing ponds and the coastal wetlands and estuaries. And then the last kind is the marine, which is the embayments, the open coastal waters like the Kihei Coast, and oceanic waters, which are further out from the shore. Under the marine bottom ecosystems, you have a lot of diversity. You have sand beaches, lava rock shorelines, and of course, coral reef ecosystems. Another concept that we need to understand if we're going to manage water quality is what is a watershed. And watershed is just simply a drainage basin. It's an area from which all the water drains to one place. And that can be drainage above ground and below ground, and it's all the water. I'm often asked when I say water quality, they're like, what do you mean, drinking water? Do you mean streams? Do you mean oceans? I mean all of it, because it's all connected. So we want to keep in mind the interconnectedness. And so a minimum, we have to have management units if we're going to manage things. And so a watershed is the minimum unit that we can manage and still actively achieve water quality goals. Because why? The in-out thing. We have to manage everything coming in on the mountain side if we want to achieve a goal in the ocean. And this may sound very familiar to you because it's very similar to a traditional Hawaiian concept of land management called the Ahapua'a system. So how do we manage this? This is the part about the regulation, the Clean Water Act. And it is a federal law, and it talks about, again, the complexity of the systems we're managing. So it's about restoring biological, chemical, and physical integrity of the nation's waters. Restoring and maintaining. And so the goals are very simply stated as fishable, swimmable waters in the beginning. Of course, it gets more complex as we look at it. So these are some of the more specific goals, and the biggest one, the most predominant one in the Clean Water Act is protect fish, wildlife, and water recreation. And that's the thing that most people that are interested in ocean water quality want to do. But there's also other supporting goals that help us reach that major goal. Things like eliminate discharges of pollution. And that led to the development of the NPDES permitting system, which is the National Pollutant Discharge Elimination System. And most wastewater in the country is regulated very strictly under that system. But in Hawaii, most of our wastewater is not regulated under that system. And we'll talk more about that later. But there's other things like researching what kind of treatments are needed and funding treatment that are also goals of the Clean Water Act. And also control of non-point source runoff, because we often think of wastewater and point sources. We're going to talk more about what that means later. But in fact, if we're going to control that whole picture, we have to look at everything, not just what comes from a treatment plant, but what's running off in our stormwater as well. So one of the ways we do that is we make those goals more specific. We do water quality standards. And standards have three parts. They have a designated use, which is saying, how do we want to use this water? Now, as human beings, often our first thing is, we want to use it for us. And so on Maui, you have things like a plan called a water use and development plan. But that plan doesn't really protect the quality, or even, it does work toward protect the quantity and preserve it for our use, but it doesn't preserve it for wildlife or aquatic life, and it doesn't protect the quality of the overall resource. So what we really need in addition to that is water quality management planning. And fortunately, there's already a system in place to do that under the Clean Water Act. Criteria is the second part of the standard. And a criteria is kind of a measure, and it can be numeric. Like we can say we don't want any more than 250 micrograms per liter of nitrogen in the ocean. Or it can also be narrative. We can say we don't want conditions that are going to grow nuisance algae. And so, and the third part is an anti-degradation policy that just says if the water quality is better than our standard, that doesn't mean we get to degrade it down to the standard. So those are the three parts of the regulations. So an example, here's a use, here's a recreational use, someone else snorkeling. And so an example criteria is that the bacteria, the fecal indicator bacteria, should not exceed 7 bacteria per 100 mil. And so here's kind of a simplification of our designated uses in the Hawaii standards. Over here you have kind of those water use and development, human-driven uses like navigation, agriculture,